Hello everyone, this is Group 3, and our topic is evolution from electronic to spintronic devices. During the course of this semester, we have studied and learned a lot of knowledge about magnetic property and its application in magnetic recording devices and RAM. However, most of students which are come from material science department is not familiar with the electronic devices we have already used in our daily life, such as smartphone and personal computer. These electronic devices, which was invented last 50 years, using the charge property of an electron, and are totally different from the principle of RAM. And therefore, I think it is interesting to understand and compare the principle of two different base electronic devices. Last but not least, we will introduce spintronic devices such as SpinFET and conventional MRAM and STT-SOT MRAM as well. Okay, first of all, let's look through the smartphone which we have used in our daily life. Those electronic device is operated with digital signal, which is known as the binary code, 0 and 1. Those signals stands for high voltage and low voltage and can be easily operated in electrical circuits. Besides, this binary signal can be calculated and connected through logic gate, forming full adder, a more simple structure to construct computer. In addition, this logic gate can be separated into different gates, such as OR gate, AND gate, and NOT gate, and this gate can be achieved by transistor. Conventional transistors such as BJT or MOSFET can be operated by source and drain, and we will discuss it more detail in following slide. Those device we have discussed previously is operated by controlling the charge density. However, we have introduced a brand new concept of electron, the intrinsic property spin. This property can give us more useful application in devices. On the left-hand side is a famous experiment related to electron spin property of electron. Scientists inject silver atoms from a hot oven through a non-uniform magnetic field and observe the atoms are separated into two bands, but not continuous bands which we had predicted in classical way. Therefore, the results confirm electrons not only have charge property, but also contains spin information. Moreover, the two separate silver atoms band can be viewed as two states, spin up and spin down respectively. Are there any applications of the spin in the electron? Of course, for example, it can operate more fast compared to conventional MOSFET, which charges accumulate in resistor or capacitor, often suffer from RC delay and non-ideal effects such as small channel effect. Meanwhile, since controlling charge in conventional MOSFET, we have to pull or push electron to modify the electron density in the channel, often consume lots of energy, making this charge-based device wasting too much power. However, using the spin-based device, the only thing we have to use is flipping the state of electron in the channel, and therefore the architecture of spintronic device is more simple and more fast and less power consumption. Now we will go through an overview of electronic device, which we have often fabricated on a silicon chip. Generally speaking, we can divide this device into transistor and memory. Transistor consists source and drain. And gate, as you can see in this picture, it is a processor. Before capping, the rainbow-like color of the surface is come from the microstructure, which caused from doping and etching on the wafer, causing light deflections and form a rainbow-like color. If we observe the wafer under SEM, we can find lots of wires distribute and connect each other, forming logic circuits. Following is the memory used for data storage. For example, DRAM, SRAM, and flash memory is widely used in daily life. Although they have the same functions, their working principles are totally different, and therefore, Different types of memory has its advantages and drawbacks, and will be used in different situations. In the right-hand side shows the device take the advantage of electron spin property, which is known as the spintronic, similar to the MOSFET, which will use the charge to control the gate. Spintronic using the gate to tune the electron spin directions in the channel, and the metal contact at the drain will detect the orientations of spin electron, causing different resistance. Therefore, we can form a field electric transistor by voltage gating, but not magnetic field. On the other hand, we can use spin property to create memory as well, since the magnetic moment inside ferromagnetic material can be stored and rewrite by imposing external magnetic field. Besides, magnetic moment orientation toward south or north can be treated as binary data. Last but not least, the orientation can be detected by giant magnetic resistance effect. Detail will be discussed in following slide. Let's introduce MOSFET first. A MOSFET consists a layer of metal and oxides covered on a semiconductor. As far as we know, in order to increase the conductivity of semiconductor, we can add dopants such as boron or phosphorus to create P and N-type semiconductor. N-type semiconductors utilize electrons to conduct, while P-type semiconductors use electron hole. If P-type and N-type semiconductor cross together, will form a p-n junction, causing neutral regions, and the circuit will not conduct through this region. Therefore, without gating, during the equilibrium state, circuit will not conduct through the channel. However, if we impose a positive voltage across gate and body, we can repel the hole under the gate and forming a special layer which is known as the inversion layer, contained with electron. Now, the electron can go through the channel while gate is under positive voltage bias. Finally, a simple analogy of field effect transistor is like a faucet. If we turn on the gate, just like we turn on the switch, water or circuit will pass through. After understanding the working principle of a MOS, we can find interesting if we combine several MOSFET in a specific way. For example, if we combine a MOS in pattern like this, the right figure can form an AND gate. If the signal input to A and B is 1 or high voltage, the circuit will conduct and the ground voltage 0 volt will go through the gate in the right hand side. The gate is under control of 0 voltage bias, therefore the transistor will not conduct, leaving the F terminal with high voltage VCC. The output will become 1 if both the input are 1. On the other hand, if one of the input is 0, ground voltage will not connect to the gate of C transistor, and VCC will open the C transistor, resulting in the ground connect to the F terminal, and the output will become 0. And this is the truth table of the AND gate. The similar analysis can be done in the same way. Therefore, we can construct different gates by connecting NMOS or PMOS with different patterns. This is a very simple introduction to the logic circuit system in the view of MOSFET. After studying the structure of MOSFETs, let's move on memory parts, the DRAM and the SRAM, which is widely used in computer components. DRAM stores binary information by charge in a capacitor besides the transistor, just like a water bucket which stores water inside. While the bucket is full of water, the data stands for 1. On the other hand, while the bucket is empty, the data stands for 0. If you want to store this data into the capacitor, first step is to turn on the transistor, and the data line is connected to the capacitor. If the data line is connected to high voltage, the capacitor will accumulate charge. After enough time, we can close the gate, and the charge will be confined in the capacitor. If we want to read the data in the capacitor, we can turn on the transistor and measure the voltage. to distinguish the signal is 0 or 1. However, there are some drawbacks. The capacitor is not strong enough, and the charge will leak after time. Therefore, we have to recharge the capacitor after a period of time, which means it is energy inefficiency. On the other hand, SRAM utilizes the logic circuit structure to combine previous states in the circuit, similar to the SR flip-flop. The data is stored in the structure and no capacitor is used in SRAM, and therefore SRAM do not need to recharge every moment. However, as you can see, the structure is more complex than the DRAM. It takes at least 6 transistors to storage a bit, but only need 1 transistor per each bit for a DRAM. Besides, DRAM and MRAM need charge and circuit to maintain the memory. If we turn down the power, those data will lose. Therefore, we call this type of memory as volatile memory. Now let's move on another type of memory, the flash. This kind of memory can keep the data after power is removed. Therefore, it is widely used in camera memory card or USB flash drive. The storage principle of flash is different from the DRAM and SRAM, and clever design is to insert a floating gate between oxide and metal contact, different from an original MOSFET. The floating gate can trap the electron, causing the threshold voltage shift. For example, if we impose a positive voltage on the gate, causing the electron in the channel attract and tunneling to the floating gate dielectric layer. After removing the gate voltage, the trapped electron inside the dielectric will attract more electron hole in the p channel. Therefore, we need larger gate voltage to form inversion layer inside the p channel, which means the threshold voltage shifts to right. We can measure the drain current under the same gate voltage. The different drain voltage shows different data storage in the floating gate. Using floating gate is different from DRAM and SRAM, which require charge. Therefore, flash is non-volatile memory, which means data will not lose after power is removed. However, there are drawbacks. Since each writing cycle requires electron tunneling through the tunnel oxide, the oxide may break down after too much writing cycles. Therefore, the endurance of flash is worse than DRAM and SRAM. After discussing electronic device based on charge property, let's move on device which use the electron spin property. First of all, I will discuss the more simple concept of spintronic devices, the GMR effect. This effect is observed in the sandwich layers of ferromagnetic and non-magnetic dielectric layer. Scientists observe that the resistance across this layer can change dramatically depends on the magnetizations of these two ferromagnetic layers. While two ferromagnetic layers' magnetization direction is parallel, electrons can conduct easily, giving a low resistance. While two ferromagnetic layers' magnetization is anti-parallel, electrons will scattering and cause the resistance increase. As you can see in the right figure, the difference between parallel and anti-parallel is about resistance is about 80%. Therefore, if we can change the magnetization direction by external field, we can store the data in the ferromagnetic layer, and we can read the data by measuring the resistance across the sandwich structure. After understanding the principle of GMR effect, let's apply the principle into the MRAM. As you can see, a bit of MRAM consists of MTJ cell and a transistor. A MTJ contains a free layer and a reference layer, or we just call it pin layer. In order to alter the magnetization directions of the free layer, we can conduct a current besides the MJT cell. Therefore, a magnetic field induced by the current can alter the magnetizations of the free layer. If we want to read the data inside the MTJ cell, we can turn on the transistor and measure the current across the transistor. On the right-hand side is the structures of a MRAM array. Something need to notice is that all the cells in the same row connect with the same bit line or word line. If we conduct a current through a bit line, magnetic moment in each cell under the bit line may flip, which causes miswrite. In order to write the specific MRAM cell in the array, we need a word line to control. Here are the figure of the asteroid figure of the MRAM cell. With the assist of word line field, we can reduce the field which bit line needs to flip the cell. Therefore, we can write the specific MRAM cell by this method.
Okay, I'm going to introduce the spin transfer torque STT. And first, I will going to introduce the MTJ, which is an important part in the STT. And MTJ consists of two ferromagnetic thin films separated by a tunnel barrier as shown in the figure on the left hand side here. There are two kinds of MTJ, an in-plane MTJ where the magnetization of ferromagnetic layer lies in the film plane, as shown in the picture A here, and the perpendicular MTJ where the magnetization direction is perpendicular to the film plane as shown in the picture B here. The resistance of the MTJs depends on the relative orientation of the magnetization in two ferromagnetic layers. This resistance change is called the tunnel magnetoresistance TMR ratio. This TMR ratio is defined by the equation down here, and the R sub AP and R sub P here means the resistance of the antiparallel and parallel magnetization configuration between the two ferromagnetic films. The magnetization direction of one ferromagnetic layer is called the pin layer, which is fixed by exchange interaction with an adjacent antiferromagnetic layer, and the magnetization direction of another ferromagnetic layer is called the free layer, which can be freely rotated. And the tunnel magnetoresistance TMR ratio we just mentioned is a magnetoresistive effect that occurs in a magnetic tunnel junction. If the insulating layer is thin enough, electrons can tunnel from one ferromagnet into the other. Since this process is forbidden in classic physics, the tunnel magnetoresistance is the strictly quantum mechanical phenomenon. This TMR ratio only depends on the spin polarization of two ferromagnetic layers. And on the right side here is one of the examples to increase the TMR ratio. They use this sandwich structure, and the this cobalt layer here were amorphous, and the MgO layer it had a highly 001 oriented polycrystalline structures. And we can see this from the left hand side picture A here. And after annealing with the magnetic field, the cobalt phase layer, the cobalt layer were crystallized in 001 direction, as shown in picture B here on the right side. And the TMR ratio increased up to 350% after annealing, and this indicates that the formation of a highly oriented 001 sandwich structure here is essential to obtain a high TMR ratio. Okay, here is the real structure of the MRAM, and the magnetic memory with the MTJ are considered as a good candidate for the NVRAM. There are two kinds of magnetic memories characterized by their writing mechanism, showing the picture. And in the left-hand side picture A here is the conventional MRAM, which is based on the magnetic field writing induced by current passing through a right word line and a bit line. This type of MRAM requires a larger current to reduce the MTJ size because the required magnetic field increase inversely proportional to the width of the MTJ size. And to control the writing in memory of this conventional MRAM, we need to control the current to flow through the certain bit line and word line. Because when we turn on the bit line, all the MTJ under this line will get the same magnetic force in a certain direction. And to precisely control the single MTJ, we need to turn on the world line under this MTJ. In the same time, all MTJ under this line will get the magnetic force in another direction. But overall, only the certain single MTJ in the cross spot will get enough force by these two lines to change the direction. Okay, and the picture on the right side, picture B here, is the STT RAM, which is based on the spin transfer torque magnetization switching. In this new type of MRAM, the right operation can be performed by current passing through MTJs, and there is no additional right word line, which leads to the reduction in cell size. Furthermore, since right current can be reduced inversely proportional to the area of MTJs, as will be explained below, STT-RAM is valuable for advanced scaling. Spin transfer torque magnetization switching was independent. Spin transfer torque reveals a new type of interaction between magnetization and a spin polarized current, which is attributed to angular momentum exchange between the spins of local magnetic moment and free electron passing through the MTJs. And here's is the detail of how it works for the STT, and we can see the picture on the left side here. The picture A here shows the from the anti-parallel to the parallel switching. In this case, the electrons should flow from a pin layer to a free layer. After electrons pass through the pin layer, the electrons with the same spin direction as that of the magnetization in the pin layer mainly remain, and the current is spin polarized. This spin polarized current is this spin polarized current exerts STT onto the magnetization of the free layer, and when the amount of spin polarized current exceeds the threshold value, the magnetization of the free layer is switched. And from the picture B here is the case of from the parallel to the anti-parallel switching. And here the electrons should flow from the free layer to the pin layer. After the electrons pass through the free layer, the electrons with the same spin direction as that of the magnetization in the pin layer pass through the layer. However, the electrons with the opposite spin direction is reflected at the boundary between barrier and the pin layer and injected into the free layer. This current exerts STT on the magnetization of the free layer, and when the amount of the spin polarized current exceeds the threshold value, the magnetization of the free layer is switched. And the picture on the right hand side here shows the switching current density as a function of the plus direction. As shown in the picture, the current density steeply increased in the plus direction region of less than 10 ns here. And this region is called the precision region, where the STT switching occurs with precision motion of magnetization in the free layer around the effective magnetic field. On the other hand, the direction region less than 10 ns, the current density can be written as the equation like here. And where here the torque zero is the temp plus y, which normally equals to 1. By fitting the experimental current density versus the natural log using this equation, can obtain the picture down like this. And the region here is we call it the thermal fluctuation region, where the thermal fluctuation of the magnetization in the free layer assists STT magnetization switching. Okay, and here the picture shows the transistor operation mode in writing, the voltage relation between the cell modes, transistor, and the MTJs. And the picture A here shows when the writing of the P state to the parallel state to the anti-parallel state is accomplished, a high voltage of VDD is connected to the free layer. For the MS, the source and substrate are connected to a low voltage of VSS. When the MS gate voltage turns to VDD, the current flows from the free layer to the fixed layer, and the magnetization of the free layer is reversed. At this time, the MS operation mode is called the source ground. And the picture B here shows the mode of writing from anti-parallel to the parallel state, and the connection to the power supply is upside in the picture A. The VSS is connected to the free layer in the MTJ, and the drain of the MS is connected to the VDD, and the substrate here is connected to the VSS. In this mode, the source voltage is the same as the voltage for the fixed layer of the MTJ. This operational mode is called the source follower. Although the gate voltage changed to VDD, VGS decreased due to the voltage for the fixed layer of the MS device, and the source voltage increased due to the substrate effect, where the voltage of the substrate to the source VBS becomes negative. Through this effect, the current the MS can flow through in the mode shown in the picture B, reduced to about half that of the current in the picture A.
Now I'm going to introduce spin orbit torque and run, which is as known as SOT and run. Before we go into the details, we should know the spin Hall effect first. Recalling the Hall effect, the production of a voltage difference, which is the Hall voltage, across an electrical conductor that is transversed to an electric current in the conductor and to an applied magnetic field perpendicular to the current, as the left picture. The Hall effect is due to the nature of the current in the conductor. Current consists of the movement of many small charge carriers, typically electrons, holes, ions, or all three. When magnetic field is present, these charges experience a force called the Lorentz force. When such a magnetic field is absent, the charges follow approximately straight line of sight paths between collisions with impurities, phonons. However, when a magnetic field with a perpendicular component is applied, their paths between collisions are curved. Thus, moving charges accumulate on one face of the material. This leaves equal and opposite charges exposed on the other face, where there is a scarcity of mobile charges. Similarly, the spin Hall effect is a transport phenomenon which consists of the appearance of spin accumulation on the lateral surfaces of an electric current carrying sample, the signs of the spin direction being opposite on the opposing boundaries. In a cylindrical wire, the current-induced surface spins will wind around the wire. When the current direction is reversed, the direction of spin orientation is also reversed. That is, this effect splits electrons with different directions of spin to the top side and bottom side, as the figure in the right-hand side. Spin Hall effect usually happens in heavy metals. The special thing is that it only separates the spin directions instead of voltage. Now we can see more details of SOT and run. As we just mentioned, spin Hall effect When injecting the current in the heavy metal layer, the spin current will be induced along the lead axis. When the spin current interacts with the magnetic moment in the ferromagnetic layer, it will result in two torques. These torques will help flip the ferromagnetic layer. This is how third generation MRAM SOT works. However, if there is only the equivalent magnetic field provided by the spin current, it cannot flip the moment from top to bottom, or from bottom to top. It can only make magnetic moment transfer into parallel level. Then magnetic moments will return random direction, which means 50% goes up and 50% goes down on the EZ axis. To prevent this phenomenon, the commonest way is to apply a field when it is flipping. Through this way, the equilibrium of vertical anisotropy can be changed. However, it is not realistic to build an applied field into the electronic component, because when device becomes smaller, the density increases. The component will become closer to each other, and thus the probability of miswriting and misreading will increase a lot. Besides, the complexity of circuit design will increase too. This is not. It will become more difficult for engineers to design the circuit. Though there is a lot spaces for SOT MRAM to improve, it has the potential to challenge STT MRAM, as it is a faster and much more efficient memory technology. It is feature switching of the free magnetic layer done by injecting an in-plane current in an adjacent SOT layer. Unlike STT MRAM, where the current is injected perpendicularly into the magnetic tunnel junction, and the read and write operation is performed through the same path.
In addition to the memory devices, we can use spintronic to create spin transistor as well. Electron injected from the source will go through the channel same as the MOSFET. However, if we can alter the spin directions transport in the channel, we can modify the conductivity of the channel. For example, initially unpolarized electron goes through the source. Electron will spin down. With spin down will scatter away. Only spin up electron can go across ferromagnetic source contact. If spin up electron can transport coherence across the channel to the collector, since the magnetization direction is parallel to the electron. Therefore, the electron can go across easily. However, if we impose an electric field across the channel, accelerating spin electron in the channel will feel a magnetic field on the electron, causing spin electron going through precession moment. If the electron under precession flips, electron will become anti-parallel and the collector causing large resistance. Therefore, we can control the transistor with the gate voltage by spin method, which can achieve the same result in the MOSFET. And here are experiment setup from this paper. As you can see, spin electron goes through the channels from source to drain. And while we impose a gate voltage across the channel, the drain voltage oscillate depends on the gate voltage. And here are short conclusions of the devices we have discussed in these presentations. And we can see that different types of devices using different kinds of principles, and they have different advantages and drawbacks. And we can find out the new generation spintronic devices have better performance and advantage compared to the traditional electronic. Therefore, scientists and engineering and companies are doing research about spintronic devices to make our life better in the future. Thanks for your listening.